All right, to start off, we're going to take some derivatives just as a warm-up. This is to get our mind in the mode of dealing with some implicit differentiation. This is for a related rates workshop. I'm going to get this part out of the way, although I guess it won't let me, so that's okay. All right, so I'm going to take the derivative with respect to time, and when I do dA dt on this side, we end up getting, okay, that's a constant, so it's going to be 2 pi r, and then I've got to have a dr dt afterwards. I'm choosing to use this notation instead of prime notation because it's going to be helpful for us later. Next up, we've got the Pythagorean theorem. So we've got 2a and then times dA dt plus 2b times dB dt is equal to 2c times dC dt. All right, then we got a volume formula. This is the volume for a sphere. So dV dt, and here we've got a constant. That becomes 3 times 4/3 is 4 pi r squared dr dt. All right, here we've got a product rule. On the other side, we've got dy dt, and the derivative of x is going to be dx dt, tangent of theta. And then we've got to do x times the derivative of tangent of theta is going to be secant squared of theta. And then we've got to multiply that by d theta dt because of the chain rule. All right, finally, I'm going to write this as 3x to the negative 1. So my brain doesn't see that as a quotient rule because we already have a quotient rule on this side. That's going to become negative 3x to the negative 2 dx dt. And on this side, that's going to be dr dt times s minus ds dt times r over s squared. We're going to be doing a lot of derivatives implicitly today, so that was a warm-up to help us kind of get our brains in that place. The goal today is to think about related rates problems. Hopefully you've already had an introduction to this. And in looking at this, our goal is to write things in terms of calculus language, to be able to interpret those expressions. Those are the two most important pieces of this for life and for me. And then setting up and solving problems featuring related rates is kind of the calculus side of this. This is certainly something that we do using calculus. And as far as the AP test, you might see one question on there that's about this. We're going to start off with some visuals. I think that's a really helpful thing. One of the most common problems that we talk about with related rates is what happens if a ladder is leaning against a wall and starts sliding down. We've got different measurements that we can take. We can talk about how far away from the wall the base of the ladder is. We can talk about how far up the wall the top of the ladder is. We can talk about how long that ladder is, and I might just call that h for hypotenuse. But then we also need to be able to talk separately about, okay, this ladder is moving away from the wall. Let's call that dx dt, the change in x over time. This ladder is sliding down the wall. Let's call that dy dt, the change in y over time. And if we had some kind of a weird stretchy ladder, we could say that it's stretching as well, or maybe squishing, I don't know. And call this dh dt, the change in hypotenuse over time. For most ladders, this is probably going to be 0. For this one, I don't know. I wanted to start this visually so that we can talk about the difference between constant values that are fixed at a specific moment in time, like x and y and h, and values that are changing, and talking about that change themselves. So these things are all changing, but the rates and the numbers themselves are two different things. And keeping those separate in our brain is going to be really important. Another problem that we frequently see deals with things like oil slicks and what happens as you're adding stuff in the center and it's spreading out uniformly. So we talk about this as having a circular area on the surface of whatever this is spreading out over. We can talk about that as the radius, which again has a set value at a moment, but that's also growing at dr dt as oil is being poured in here, and we're going to call that dv dt for the change in volume over time. The beginning aspect of kind of diving into these actual related rates is to begin talking about the way that we write rates in calculus and taking a minute to kind of get used to writing these rates. So pause this for a second, try to get these three rates down on paper, and then I'm going to go through that. All right, the first one we got, Jonathan is growing at a rate of 3 inches per year. This is about height, so I'm going to call this dh dt. You can use whatever letter you'd like. 3 inches per year and growing, that's going to be a positive rate. So we're going to call this at 3, and then I'm just going to use my units. My bank account is shrinking. Okay, that's not good. At a rate of $4 per day. So that's going to be, first of all, a negative rate because we're shrinking. And then I'm going to call that $dt for my amount of money in the bank. And that's going to be negative $4 per day. Okay. Third one, water is being pumped into a tank at a rate of 2 inches cubed per second. First thing I notice is that this is a positive number. Water is coming in. The second thing is that with inches cubed, this is a volume unit. So we're talking about dv dt, and we're told that that's 2 inches cubed per second. We're going to make this a little bit more complicated by moving this to deal with some geometry stuff. First off, we have a rectangle. I'm going to call this the width and the length. And the first part of this is writing some different formulas for us. So like perimeter is going to be 2w plus 2l. Area is going to be w times l. So we can talk about the change in perimeter. We've got to take the derivative with respect to time. So that's going to be dp dt is going to be 2 times the derivative of w dw dt plus 2 times the derivative of L, dL dt. Side note, I'd like you to notice that I haven't plugged in these values. I'm just going to call this 5 and 8 just so that we can keep that in mind, but we're not plugging these in because we're talking about the perimeter changing, not what it is right now. Same thing for area. So we're taking the derivative here. We've got dA dt. And that's a product rule. So I'm going to do the derivative first, dw dt times the second, plus the derivative of the second, dl dt times the first. Okay. So we've got some expressions. We're being told some things here. We're being told that the length and width are increasing at 2 inches per second. That's for these two problems here. So that means that dl dt is equal to 2. dw dt is also equal to 2. This is positive because it's increasing. And I'm also going to bring in this information. So we've got w is equal to 5 and L is equal to 8. Depending on the way that you set up your rectangle, you may have these reversed. That's totally fine. For part 3, that means you'll get different answers, but I'll talk about both versions of that when we get there. Change in perimeter. I'm going to plug these values in now. So I've got dp dt, and we have a formula for that. 2 times dl dt, which is 4, plus 2 times dw dt, like that I said those backwards, which is also 4. That's going to be at 8 inches per second. For the change in area, we have a formula for that as well. It's going to be dw dt. So dA, I'm going to run out of space here. I'm going to try to write real small. dw dt is going to be 2. The length is 8. Plus dL dt, which is 2, times the length is 5. That's going to end up being 16 plus 10 is 26. And here we've got inches per second times inches. That's going to be inches squared per second, which makes sense for an area rate for us. For part 2, we're now decreasing, that's negative, at 2 inches per second. So now this is going to be dl dt is going to be negative 2. dw dt is going to be negative 2. I'm going to keep those things the same, W5 and L8. You might notice that this is going to be the exact opposite of what we had here because we're changing the sign of just these pieces, which makes everything here negative, but otherwise we're keeping the same thing. So I'm just going to do this as negative 8 inches per second, and the area is negative 26 inches squared per second. For the last part, now we are increasing its length by 3, so dl dt is going to be 3, and its width is decreasing by 1, so dw dt is going to be negative 1. Based on my values of w equals 5 and L equals 8, we're going to get certain values in this problem. You might get different values depending if you switch those around. We'll talk about those again when we get to the area part. Change in perimeter. So dp dt is equal to 2 times dl dt, which is 3, plus 2 times dw dt, which is negative 1. That gives us 6 minus 2 is 4, and that's in inches per second. Change in area, dA dt, and again, this is using these values. That's going to be 3 times 8 plus negative 1 times 5, which is 19 inches squared per second. If you had done L equals 5, W equals 8, then we're going to have some slightly different things. We'd end up with, I like that I switched these things around and did the opposite ones in the last one. So this is actually the answer for this. And for my original values, which I did not do correctly, we've got dA dt is going to be 3 times 5 plus negative 1 times 8, there we go, is going to be 7 inches squared per second. So for problems that you're being given that are unclear as far as which dimension is which, that can be a mess. For anything that you're assessed on, you will absolutely be given something that is very clear which dimension goes with which. All right, last piece of this, we've got a right triangle. We are looking for some areas and hypotenuse values, and then we're not going to use this to solve anything. So we're just thinking about this in terms of setting things up. So for a triangle, I'm going to draw a picture first. I'm going to be smart and call this X, Y, and C, so I don't have two A's in this problem. The area would be 1/2 XY. The change in area, so we've got dA dt, would be 1/2 the derivative of x is dx dt. Y plus 1/2 the derivative of y is dy dt. X. Cool. For the hypotenuse, we've got x squared plus y squared is equal to c squared. Change in hypotenuse is going to be 2x dx dt plus 2y dy dt is equal to 2c dc dt. That leads us to a place where we're able to kind of talk about a whole set of strategies for solving problems that involve related rates. The first thing that we really need to do is to draw a picture, and hopefully you're a better artist than I. Labeling this using variables just so that we know things that are changing and things that are known at a specific moment is really important. Going through the problem, listing everything that we know and everything that we don't know, any formulas, especially geometry, that might tie into the problem, If you have taken physics, this is going to sound really familiar to setting up a problem in physics, and is super applicable to that and to everything that we do here. Identifying anything that you know that is not changing. Think about that ladder we had in that first visual example. The length of the ladder is not changing. If you were to plug that length into the problem at the beginning, you eliminate a variable that isn't actually a variable, which is a good thing. If you were to plug in something that is changing, like the length of the ground, and then you try to take a derivative, that's going to go to 0. That is not helpful for us. Differentiating with respect to time, so taking the derivative, knowing that everything is going to require implicit is really helpful here. That also gives us expressions that we can talk about as things like the ADT, the change in area over change in time. This looks like a slope, it looks like a rate, and that's a really helpful way to think about this. Once you've taken the derivative, plug in everything that you know. Now is the time to plug in those constants, and getting to just solving for like the ADT is where we're going to go from there. Let's look at a few examples of these things. Hey, look, an oil tanker. All right, so I'm going to go from the beginning. So we've got a circular pattern whose radius increases. Okay, so before I even finish this problem, I'm going to start writing some stuff down. I know that circles involve circumference, 2 pi r. I know that they involve area, pi r squared. And radius increases at a rate of 50 feet per minute. Okay, that sounds like a positive rate. And this is going to be a change in radius, so dr dt. I'm going to write that down. dr dt is equal to 50. How fast are both the circumference? Okay. That's asking about dc dt. And the area of the spill, okay, it's asking about dA dt. Increasing when the radius of the spill is, all right, so we have two different radii to use. R1 is 20, R2 is 50. I'm going to draw my picture. And my radius is increasing. dr dt is equal to 50. All right, I feel pretty good about this. I've got some stuff written down. I scribble all over my problem. That's usually a good sign. And I have a picture to kind of explain what's going on here. Let's finish taking these derivatives. So the derivative of circumference, 2 pi is a constant. So this is 2 pi dr dt. First thing I notice is that I don't actually have an r variable in there. So in either of these cases, the actual radius doesn't matter, because dc dt is going to be equal to 2 pi times the dr dt value, which is 50. So that's going to be 100 pi, and this is going to be feet per minute. The reason that that doesn't change is because I don't have r left in here as a variable. I just have dr dt. Okay, let's look at my area. So again, pi is a constant, so the derivative of area with respect to time is going to be 2 pi r. Implicitly, we have to include dr dt. Here we have both an r and a dr dt. So if we think about this for r1, which is 20, then dA dt is equal to 2 pi times 20 times 50 feet squared per second. And that's going to be, I don't know, 50 times 2 is 100, that's 1,000, 2,000 pi feet per second, feet squared per second. For R2, which is 50 feet, dA dt is going to end up being 2 pi. Instead of 20, now we have 50. And then we have 50 again for dr dt. And this again is going to be feet squared per second. 50 times 50 is 2,500 times 2, 5,000 pi feet squared per second. Oof. Oh, no, look, we've got a ladder problem. I'm going to draw my picture. So you've got a 13-foot ladder. Okay. Leans against a vertical wall. The lower end of the ladder is pulled away at a rate of 2 feet per second. So this distance is growing at 2 feet per second. I'm going to call that dx dt. How fast is the top of the ladder coming down the wall? Okay. So that's going to be dy dt. And I don't know what that is. The instant the top is 12 feet above the ground, okay? So that tells me that y1, because I see I have two of these, is going to be 12. And I've also found that y2 is going to be 5. All right, so looking at this, I've got a way to connect these three lengths. That's going to be with the Pythagorean theorem. So we've got x squared plus y squared is equal to hypotenuse squared. I also know that my hypotenuse, the ladder, is not changing. So I'm going to just plug that number in. 13 squared is 169. Okay, let's take the derivative. We got 2x dx dt plus 2y dy dt is equal to 0. And by plugging this number in at the beginning, I don't have to deal with an h in my final expression. I am going to have to figure some other stuff out. So for example, I know y1 at 12 feet. I know the hypotenuse is 13, and the person who designed this problem decided to give us a special right triangle. This is 5, 12, 13. So x1 would be 5 by the Pythagorean theorem. x2, if we've got 5 and 13, that means that this has to be 12. So we're just switching the x and the y, going from part to part here. All right, plugging some stuff in. I'm going to do y1 first. Didn't mean to just erase stuff, but I clicked the button. Okay. So we're going to do that one first. And we've got 2 times 5 times dx dt is 2, plus 2 times 12 times dy dt is equal to 0. Getting that stuff by itself, 2 times 5 times 2 is 20. We get negative 20 divided by 24. Feet per second is going to be dy dt. Doing this one, we're going to have 2 times 12 times 2 plus 2 times 5 times dy dt is equal to 0. We end up with 48. So that's going to be negative 48 over 10 feet per second is equal to dy dt. So it's interesting because this rate is increasing as it gets further down the wall. All right, so looking at the next one here, we've got a camera mounted. I'm going to draw a very accurate camera. 3,000 feet from a launch pad, so this is 3,000 feet. And the goal is to keep the space shuttle in focus, so I'm assuming this space shuttle, again, very accurate space shuttle, it's going to be there. It's vertically rising at 800 feet per second when it's 4,000 feet high. So I'm going to call that dy dt is 800 feet per second. And at that time, we're going to say y is 4,000 feet. How fast is the camera to shuttle distance? So if the shuttle is here, we're really talking about the hypotenuse of a right triangle. And here, at we're at 300 instead of 3,000, we're looking at something like this. All right, so let's take a look at this. So we've got a right triangle where we're looking for distance. Pythagorean theorem makes sense to me. So let's go with x squared plus y squared is equal to h squared. In this case, the x distance is 3,000. That's not changing. I'm going to plug that in here, although I know I'm not going to actually need to do that out. My y distance is changing, and my h is changing as well. So I'm not going to plug those values in. Let's take some derivatives. Derivative of a constant is 0. We get 2y dy dt, and that's going to be 2h dh dt. All right, so we also didn't actually figure out h earlier. We've got 3,000, 4,000. That tells me this is going to be 345. So that would be 5,000. Okay. Now let's plug some stuff in. So we got 2 times 4,000 dy dt, which we know is 800. And then we've got 2 times... that's right, 4,000, which just messed me up. 2 times 5,000 times dh dt. And that's what we're really trying to figure out here, is how fast that distance is changing. Doing some elimination of stuff, we got 3,200 is equal to 5 times dh dt. I'm going to write that up here. So solving that, we end up getting 3,200 over 5, and that's going to be feet per second is equal to dh dt. Next up, we got sand being poured on a beach, creating a cone whose radius is always equal to twice the height. That's a really important thing for us to notice. That's giving us a second equation to use. And the reason of that is that the equation for cone volume is going to have both an R and an H in it. And if we don't deal with this now, we don't have a way to kind of deal with that later. If the sand is poured out at a rate of, this is a volume thing, so let's call this dV dt, is being poured onto this cone, so it's growing. Okay, so this is positive 20. How fast is the height changing? dh dt is question mark when the height is, and we have two different examples again. So let's go with h1 is equal to 2, h2 is equal to 6. Okay, we're looking at a volume of a cone. So I'm going to start with that formula. Volume is equal to the base area, that's pi r squared, times height times a third. Anything pointy is times a third. Cool. The other thing that I notice is that we're given stuff in terms of h. We care about dh dt. It might be useful to substitute h in for r. That's why they gave us this equation. So v becomes pi 2h squared is going to be 4 times h squared times h times 1/3. So we could rewrite this as pi times 4/3 times h cubed to make that a little bit easier for us to process. The derivative of that, so dv dt, is going to be, bring the 3 down, this is a constant. 3 times 4/3 is going to be 4 pi h squared times dh dt. Let's plug stuff in. So for h1, which is 2, we end up getting dv dt, which is 20, equals 4 pi times 2 squared times dh dt. Getting dh dt by itself, we get 20 over 16 pi is going to be dh dt. Looking at the second version of this, where we've got h is equal to 6, same start, we've got 20 is equal to 4 pi, 6 squared is going to be 36, and then dh dt. Solving that, we get dh dt is equal to 20 over 4 times 36 is 144 pi. And that's it. Oh, look, we got another cone. So we got water draining from a conical tank at 2 meters cubed per second. Let's go with a cone going this way. Okay. So when we see this, that's going to be dv dt is going to be -2 cubic meters per second. Cool. The tank is 16 meters high, and its top radius is 4 meters. This is a really important thing. Because this is a tank, that ratio is going to be the same all the way down. So if we're looking at 16 height to 4 radius, that means that the height is equal to 4 times the radius. This is going to be the only way that we can really deal with kind of getting some of these variables out like we did in the previous problem. And we're looking at how fast the water level is falling. That's a height question, so dh dt. When the water level is h1 is going to be 12, h2 is going to be 2. Okay, I'm going to use the same math that I did in the previous one. Start off with my volume is pi r squared times h times 1/3. We've got a different relationship here in terms of the height and radius, so I'm going to plug that in now, but I really want this to be with height. So let's write this as height over 4 is equal to radius. So v is equal to pi radius squared would be height squared over 16 times height times 1/3. Simplifying that a little bit, we've got v is equal to pi over 16 times 3 is 48, h cubed. Taking the derivative, we've got dv dt is equal to 3 over 48 is going to be pi over 16 h squared times dh dt. All right, we're told that dv dt is 2, and we've got some stuff to solve. So let's do h1 first. So we get 2 is equal to pi over 16. H squared is going to be 144 dh dt. Getting that by itself, 16 times 9 is 144. So we end up with 2 over 9 pi is equal to dh dt. Should also be -2, which means that's -2. That means that we are going down at a rate of at a rate of 2 over 9 pi meters per second. For the other value, when h2 is 2, so we're way down there now, I'm going to do the same thing. So here we've got -2 is equal to pi over 16 times 2 squared is 4 times dh dt. That's going to get us -32 divided by 4, -8 over pi is equal to dh dt. So that means that when the height is 2, we are decreasing at a rate of 8 over pi meters per second. For the next problem, we've got a spherical hot air balloon. Air is being blown to the volume at a rate of 2 feet cubed per second, so that's v is equal to, that's dv dt. I almost screwed that one up. dv dt is 2 feet cubed per second. Find how fast the radius of the balloon is changing when the radius is 3 feet. So we've got r is equal to 3. Sphere volume, I'm going to say volume is equal to 4/3 pi r cubed. And we're trying to find how fast the radius is changing. So dr dt is what we're looking for. Let's take a derivative. We've got dv dt is equal to 3 comes down, so we got 4 pi r squared dr dt. Plug some stuff in. we've got 2 is equal to 4 pi. The radius is 3 feet, so times 9 dr dt. That gets us 2 over 36 is 1 over 18. 1 over 18 pi feet per second, I like I wrote 3 instead of second, is equal to dr dt. Ooh, surface area. So if we've got A is equal to 4 pi r squared, dA dt is going to be, bring that down, so we got 8 pi r dr dt. And here we get to use the value that we just found. So looking at this, we've got 8 pi r at the same time is going to be 3. Dr dt we just calculated, that's going to be 1 over 18 pi. And when I combine those numbers, we get dA dt. That's going to be 24 pi over 18 pi. So 24 over 18. And that's going to be in feet squared per second. Looking at our next problem, we're looking at a 12-foot ladder standing against a vertical wall. The lower end is being pulled away at 2 feet per second. So I'm going to call this dx dt. How fast is the top of the ladder coming down? At the instant, it is at 6 feet above the ground. So y is going to be 6. dy dt is what we want to know. And we can figure out x by doing some Pythagorean theorem. I also noticed that we've got the hypotenuse is double this side. That only happens in 30, 60, 90 right triangles. That suggests that this side is going to be 6 root 3 as far as a length. Okay. We're going to start with Pythagorean theorem. So we got x squared plus y squared is equal to h squared. That's a constant. I'm just going to plug that in because that length is not changing. Taking some derivatives, 2x dx dt plus 2y dy dt is equal to 0. I'm going to plug some other things in. 2 times 6 root 3 times 2 plus 2 times y is 6 times dy dt. Solving for dy dt. We end up with 2 times 6, 12 times 2 is 24. 24 root 3 negative over 2 times 6 is 12. So negative 2 root 3 feet per second. Here we've got a cylindrical tank, and we're talking about water level. So we're talking about dH dt is what we're looking for. All right, there's my cylinder. And radius of 6 feet. Okay, that's something that doesn't change because it's a cylinder. And it's being drained at 3 feet cubed per minute. So dV dt is going to be negative 3. Okay, let's see what else we might need. So we've got the volume of a cylinder is going to be the base area. So that's pi r squared times the height. We know stuff about the radius. So let's call this v is equal to 36 pi times height. And I can do that because the radius is not changing throughout this entire thing. So then when I take the derivative, dv dt is equal to 36 pi, and the derivative of h is going to be dh dt. That's what we're looking for. I used my radius. I'm in pretty good shape here. So negative 3 over 36 pi is equal to dH dt, and that's going to be in feet per minute. All right, we got a street light on top of a pole. By the way, this is the hardest problem here just because we are not great at similar triangles, and that's going to be an issue. So I'm going to call this the street light with my excellent drawing. And we've got a Yeti somewhere over here walking away. The trick is that the light here is going to cause a couple of weird lengths to happen. We're going to have a length going from the light pole to the Yeti. I'm going to call this X. And then we're going to have a length of the shadow. I'm going to call that S for shadow. The height of this is not going to change, so that's going to be 10. The height of my Yeti is not going to change either. That's going to be 6. Cool. Other stuff I see. Walking away from the pole at 4 feet per second. So that's going to be dx dt is equal to 4. And we're talking about the tip of the Yeti's shadow. So this distance here, which is going to be based on dx dt, because that's how far the Yeti's moving, added to how fast the shadow is growing. So we'd like to know dx dt plus ds dt. And that's the weird part about this. All right, so the other thing that we know here is that we've got a right angle, and this angle remains unchanged and is in both, I'm going to call this the big triangle, which is going to be x plus s, 10 and some value there, and the small triangle, which is going to be 6 and just s there. And because we have two angles equivalent in each, these are going to be similar triangles. That means that they're going to be proportional to each other. And I can set up a proportion that might look something like this. I'm going to go with x plus s over 10 is equal to s over 6. The reason I chose to set this up this way is to avoid doing a quotient rule dividing those two. I think that's a little bit easier for us to process. Okay, let's take some derivatives. Let's see if we have all the stuff that we need. The derivative of x plus s over 10. Actually, you know what? Let's multiply both sides by denominators just to kind of deal with this a little bit easier. So the derivative would be 6 dx dt plus 6 ds dt is equal to 10 ds dt. Okay. I know dx dt is 4, so that's going to be 24. I'm going to move that to the other side. Is equal to 4 ds dt, which tells us that ds dt is equal to 6. Cool. Looking at this problem, if we're looking for dx dt plus ds dt, we get 4 plus 6 is equal to 10 feet per second. So the tip of the Yeti's shadow is moving at a rate of 10 feet per second away from the pole. All right, here's a really old AP problem that should look pretty similar for us because we've got all kinds of things in terms of cones. We've looked at a few problems that are conical in nature. So we've got this open cylinder. The height is 10, and the diameter of the opening is 10. Okay, that means my radius is 5 at the top. So I'm going to look at the same type of thing in terms of this, where I've got the height is equal to 2 times the radius. And that's going to help me kind of deal with stuff in a minute. All right, so the depth is changing at a constant rate. So now we know dh dt is equal to negative 3/10 centimeters per hour. Cool. So find the volume of water in the container when h equals 5. That sounds a little bit too easy for us. That doesn't sound like calculus. So we've got pi r squared times h times a third because it's pointy. We've got h. When h is 5, that means that r is going to be 2.5. So v is going to be pi times 2.5 squared times 5 times 1/3. And this is going to be in a centimeters cubed unit. I do not need to simplify any of this. This is an AP test question, so this would be fine as an answer. I'm also going to start the bottom question above because it gives us some room. So we want to find the rate of change of volume, dv dt, with respect to time, when h is equal to 5. So I might start from my volume equation. And when I do that, since we're dealing with h, let's change this formula so that r is equal to h over 2, so I can plug that in. So v is pi h over 2 squared times h times a third. All right, we're going to combine some stuff. So we've got pi, 2 times 2 is 4 on the bottom, times 3 more is 12, and then we got h cubed. Okay, taking the derivative, dv dt is going to be, bring the 3 down, we get pi over 4 instead of pi over 12, times h squared times dh dt. This time we know dh dt is negative 3/10, so we can write this as dv dt is equal to pi over 4. H is going to be 5, so that's 25. Then we got negative 3 over 10. We're going to do some canceling here, but I don't really particularly care about this. And for volume changing over time would be centimeters cubed per hour.